who are in room 1, parallel room 1, is Sifis Koseoglu here, the chairman.
Yes, I'm here.
Okay, good. Hi,
everybody.
You now co-host, and I'm also changing every one of the speakers to be co-host, so please get started.
Thank you very much. So the last session of the conference will start with Josep Perelló.
Yes, I'm here.
Okay, thank you very much. Who will present the statistics and stochastic interest rate models for climate change mitigation. So you may start.
Okay, thank you. I will now share the screen. I will start.
Yes, please.
Yeah, okay. Now, I think that now you should be able to see my presentation.
Yes. Please make it okay.
Okay.
No, not the other way. Now we are able to see the presenter viewer.
Okay, so just a moment then.
Change the monitors.
Just a moment, sorry.
That's okay. Great.
Now, so now can you see it well, or again? Is that okay?
Now it's okay.
Okay, thank you very much.
Please proceed.
So I will start. So my presentation that is on climate change and specifically on the statistics related to what is called the stochastic interest rate models, and especially what is called discount. Okay, so just briefly, let me just present the reasons why this approach should be interesting. So it can be framed within the field of what is called the economics of climate change. And also the objective of this area or this field is to inform policies that governments might consider in response to climate change, and specifically to build climate actions. And the number of factors that are just there involved are quite diverse. So on one side, so we are looking for long-term effects. There are effects that are uncertain, so we don't know the dimension of that effects. And so they are intergenerational in the sense that many people might have a work here, and maybe they will perceive the factors differently, maybe if you're younger or you're older. And finally, also the benefits and cost of these efforts to mitigate climate change and the disasters associated to that might be distributed in a quite unequal manner, even in time and even across countries. No, this is an example from that picture is quite evident. Maybe in Barcelona, that's a quite very strange situation that we will never expect, but maybe in other countries that this might be seriously and very relevant. No? So in that sense, a possible approach to face this problem is to define and to talk about what is called the discount. Okay, so the discount in a way is a way to assess climate change impacts and mitigation policies in a way that it involves and allows to compare different points in time. So in the sense that we can have a connection between the current and present investment that we really need to mitigate future disasters, let's say, like for instance, problems with lung cancer or hurricanes, increase of temperature, viruses, no? So also it has been related to climate in some way or another. So, or even floods, no? So many general situations that in a way or another, we need to act today just to avoid serious impacts in the future. Okay, so that's more or less what is called the discount. And the idea is to connect these two worlds, no? The future world and the present world, even if we don't know exactly which are the future impacts of these acts. And so the discounting itself, the action of discount, okay, so is trying to convert, no? To convert these impacts to what is called the present day value. And this generally mathematically, one of the possible approaches are through these three equations. That the first one is more or less trying to understand that there is a rate which is also being used in many other financial aspects that we are integrated that through today until a possible future at time t. And then, since there is a lot of uncertainty there, and we consider there is a rate that is uncertain by nature, so we have an average on that. So this is the kind of operation. So we have an integration of a stochastic process, and then we have an exponential, because we are considering always here this kind of effects that are very vastly shared in science, in finance. And then we have an average. No? And then what we can also do is to define what is called the discount rate. So this is, in a way, let's say, a kind of interpretation per unit time of the cost that it could be important for mitigating future impacts in climate. No? And also there is another very important indicator that is generally used by economics, is that we just imagine that this time is very far from today, and then we can also understand the future, no? And we can define this rate as the long-term the long run discount rate, which is also defined. Okay, so this is the general frame, and then it comes the debate. So the debate that is currently happening in this context, and especially those people that are working with the discount with this climate economics, is that there is two confronted visions here. One is what is called the Nordhaus, which is one of very well-known economics in this context, that is also insisting on the fact that yes, there might be an impact, but also we might expect that we will have better tools in the future to face climate and climate disasters, no? And in the sense that also he is also saying that there is no right to consider climate change as something more priority, that has higher priority than other possible investments today. Okay, so this finally leads to generally to a discount rate that is quite high. The long run discount rate is about 4% based on his estimates. But there is another perspective that is also linked to the picture that you can see on the other side, is that present and future generations might have equal resources and opportunities, and the future generations need to have a voice to current policies. In a way or another, this also means that we need to look for lower discount rates. So lower discount rates is putting in a better balance the effects today and the effects on the future. So in a way, it's enlarging the expectation of big impact of future climate disasters to present. Okay, so the general message here is that the debate is that some people think that discount rate is very high or should be high, like 4%, and others think that it should be much lower. Okay, but and we were wanting to contribute to this discussion somehow. Okay, so if we as physicists, we like very much to approach from an empirical perspective, and one possibility is to look at what is called the real interest. Real interest is an empirical inflation adjust rate to the bonds, to the yield bonds. Okay, so in a way you are combining the bonds, the consumer price index, and then you can construct what in finance is called the real interest. That's just a difference of these two rates. And then you can look at historically what has been happening in past. And you can see that here in 3 countries that you can see very different scenarios, but there is something quite clear that in all cases you might have negative rates that generally, for instance, in the case of Nordhaus, they never consider the possibility that these rates might be also negative, which means that also the future is much even more important than present in a way. Okay, so mathematically, there is a possibility to consider a model that in physics we call it Orson-Uhlenbeck, but people from finance, they call it Basicek model, and you can evaluate and construct the discount rate on this model. Okay, so and finally you can get these numbers that you can see below. No? So a very basic message in all these formulas is that rates might be negative in this model, and they fluctuate around the kind of mean that is this M here. Okay, so but in the end, if you look at the long run discount rate, you just discover that also the noise itself lower the rates naturally. So it's not that simple just to consider an average rate looking at the past, but also you also have to include in this calculation the effects of the noise, which are mostly represented by K. So that's more or less the mathematical approach. And then I want to show you some other features, empirically driven, that are saying in a way or another that we can find several interesting scenarios based on this model, on the Orson and Lindbergh model. So this, what we did is just to map out several countries that might represent several scenarios, okay, and their own historical data, and then map out these points and see where countries where they are just falling in this big and complex, let's say, map. Okay, so in this map we can identify 4 regions. Basically, one of them are divided with this straight line, which in basically is saying that in this part here, in the lower part, we have not negative rates, or let's say not exponential decay rates, not like the 4%, but even much lower, and even they might become even, let's say, even so bad that are in just in the opposite situation, that they become even more intense, so that they are even evaluating much more in a much more intention, in much more value the future in comparison to the present. No? And also there is another driving force, which is also considering the possibility of having negative real interest rates. Okay, so but that's another thing. So the general message here is that all countries are falling in this part of the plot. Okay, and in the place that is more linked to what Stern is suggesting, and just that saying that the future has really has much more impact based on the historical data. Okay, so there is only one case, which is the case of Netherlands, that is just a little bit up to this big straight line. So one can go a little bit further and also look at the rates, at the discount rates based on different time horizons. So let's say that whether we have to invest at 10 years in the case, for instance, of Netherlands. So it has an equivalent of 3.5% ratio. Okay, so which is even in this case, it's lower than the Stern case. But if you go further, in the case of Netherlands, for instance, you are in a situation that is even larger than 4%. But if you go to other cases, you will just discover that you go to rates that are even negative, as I said before. So cases, for instance, of Germany that has been living a very bad economic situation during the 20th century might face that are just in a situation that they might see the future in a much more urgent manner than, for instance, Netherlands. Okay, so these curves here are just taking the estimation of data based on maximum likelihood methods, and you can see that countries might look very differently. And if you look at the errors, you can see in the other side of these slides this gray area that is just considering the possibility of considering the error bars and the data estimation. So these are more or less related to the sigmas related to that. And you can see that the errors also have very different impact. But also in the case of USA, for instance, the States, which is a quite very famous example, you can see that the discount rate fluctuates among 1 and 1 point something, which is far below the Nordhaus scenario. Okay, and even if you consider the errors, you're still below these values. Okay, below 4%. Okay, so just to finalize a little bit my presentation. So these are just the final sketches, as I said, so that can also bring some final messages. So first of all, the Orson-Lindbergh model is based on this data that is being observed, and that there is a possibility of having negative rates. Okay, and this model considers that. Not all models in economics in this context are considering this. And finally, also, you can make a very simplistic view by just taking into consideration the average, the historical average and just say that that in the case of USA is just 3.3% or 3% in UK, or just the average of all 14 countries that we have been analyzing is 2%. But just be careful, because also you have also to introduce the effects of the randomness, of the uncertainty that is behind this kind of models. And then you can see that the long run discount rate just can go much lower than this 3% in the case of USA, for instance, and goes to 1.8, for instance. No? And also in these columns, you can also see the size of uncertainty itself. So even all these kind of estimations needs to be taken very carefully, and just by taking this very simplistic model that is just considering finance, not considering any climate knowledge or any considering the specific knowledge about the rise of temperatures, or for instance. No? So that's more or less what I was wanting to present. So that's also has taken a shape in a paper that has been published recently in Journal of Statistical Mechanics. These are my colleagues. So myself is Josep Perelló, but also this is a joint work made with Miquel Montero, Jaume Masoliver, Doyne and Geanakoplos. And this is also part of a much more broad research that we are doing in this context, that is being published in Physical Review, but hopefully is going to be also published in Economic Journal very shortly. So thank you for your time, and I will stop my presentation here.
Thank you very much. Are there any questions? Well, there is a question on the chat.
Okay.
Could you please, Joseph, read it?
Yeah, sure. I'm trying to find the chat now because I expanded
it's in the middle. It's in the middle.
Yeah. But okay.
Okay, I can read it for you. While exponential models for lending is really common, economic growth measured in GDP hasn't kept up with the exponential model.
So I did some modeling and tried to fit some differential equations to GDP. And I noticed that like differential equations which yield polynomial solutions or fractional polynomial solutions have a way better fit than exponential model by itself. So this is a huge problem for sustainability, because if we do our economic math in terms of exponential, the economic will eat up all the real growth, which is slower than exponential. So I wanted to see how this kind of financial sustainability plays into the discounting, if it poses a problem or not.
No, it's just, well, it depends on what position, even political position you have in the climate, okay? So if you go for exponentials, so we are putting the position in that is not that urgent to go to climate action. But even if you have polynomials, that we have also been playing a little bit button on this, you have even a much more drastic demand for acting in a shorter time period. Okay, so yes, and it is possible to solve that in other forms totally. No, so it's just a mathematical expressions. And the only reason to use these models is because they are simplistic and they are already accepted in the mainstream in this context.
Thank you very much. I think that we have to proceed with the next talk. Thank you very much. So the next talk will be given by Sanda Kaufman. So you may proceed. Share your screen, please.
Yep. Works?
Yes, it works.
Good. Okay. So this is another climate change related article, and it links action to mitigate climate change with the regional impacts on the employment distribution in the region where we act. And our team includes a physicist, a policy analyst, and the geographer. So it's interdisciplinary work. So I'm going to talk to you about generating anticipatory scenarios of regional employment distribution. And then I'm going to show you a test case in Northeast Ohio for setting land aside for forestation. And then I'll mention what we plan to do next. So what are anticipatory scenarios for complex systems? You probably all know. They are tools for exploring what might happen if we do nothing or we intervene. To illustrate this, we're looking at localized policies. Somebody in an economic region does something in one city, but we think it may affect the entire region in time, in specific cases, and it may create winners as we intend, but it also creates losers, and we want to know where and what losers, what winners, and can we see predictable surprises coming, in the sense that there is a negative impact and we would like to anticipate it and maybe mitigate it before we implement the policy. So our spatial jobs location model that we're using in order to explore this problem basically says an economic region's localities form a network. So what happens in one place affects another place. And in time, jobs migrate from less desirable places that have market potential below average to more desirable places that have market potential above average. And I'm going to show you how we define this. So to generate the scenarios that we're going to look at, we compute yearly for each of the localities in the economic region its proportion of the total number of jobs in the region. We do this yearly, so it changes from year to year. So in the model, we assume that the jobs migrate as I described, and we are saying that at any place or locality X, the rate of change of the proportion of jobs in the region is given by the formula that you are looking at, where delta T and tau are taken here to be 1 year, the time period that we're looking at. And the market potential that I mentioned, which drives this model for any location X at time T, is given by the sum that contains the respective proportions and the matrix Q XY of interactions between any two places X and Y. And this model has four database parameters that we're estimating, and we're using them to build the QXY matrix in this way, where dxy is the distance between X and Y, and the other parameters are constants for the model. So now we wanted to know whether the model actually works. So we validated it on the Northeast Ohio economic region by using data from 2001 to 2015 for jobs at each locality out of the 261 that there are in the region. And we used the first 2 years to estimate those four parameters that I just showed you. And then for the years 2003 to 2015, we compared our predictions to the actual data. And you see in the leftmost corner, the actual proportion of jobs in each locality. And then in the rightmost corner, you see the model predictions. So they look pretty close, right? But we wanted to know whether they really are, and we computed the correlation. So each point in time, we correlated the 261 localities between predicted and actual. And you can see that in the year 2015, the correlation is still more than 0.98. So we got courageous and said, how about we look at forestation for climate change? And we know that it is part of the 2015 Paris Agreement. And the Earth could support 25% more trees than the last count in 2015. And it could actually reduce atmospheric carbon by about 25%. So this reduction could cancel half of all the carbon emitted by humans since 1960. That sounds pretty good. Certainly foresting Northeast Ohio won't do the trick, but it's going to be part of this effort. But we need to anticipate when we take land out of the region to set aside for forestation, so it cannot be developed, whether it impacts jobs in the region, so that we prevent predictable surprises. So here are some local criteria for forestation. We need a minimum size land area to sustain healthy forests. And below this minimum, a number of trees won't form a healthy forest. And we need a minimum distance from an existing forest, again, to sustain and expand the ecosystem because it needs connectivity. So we proceed. This is our case study, by the way. Northeast, you can see where Ohio is in the United States, and you can see where Northeast Ohio is in Ohio. And this region has 8 counties, 261 municipalities, and quite a bit of vacant industrial and commercial land. It's so-called legacy city, in other words, that decline because past the industrial era, it's lost population and industrial activity. So there's a lot of vacant land. And so we thought, why don't we basically identify vacant land parcels in Northeast Ohio that are by the 2 criteria that I just showed you. And this is an example for a piece of the region that you can see in the map. And then we used, again, Northeast Ohio employment data. They are publicly accessible. And this time, because of the data about vacant land being available only starting in 2014, we used 2012 to 13 to compute the 4 model parameters. And we assume that at each location, the industrial commercial land is proportional to the, we needed a link between land and jobs, right? We assume that industrial commercial land is proportional to the number of jobs at any particular location. And our assumption is supported by the correlation that we computed for the region. So this is how we link jobs to land. So now we're looking at anticipated employment winners and losers. We set aside land in 2014 and we checked impact on regional jobs distribution every year until 2024. We didn't want to do more than 10 years, though we of course could. So here is the do nothing scenario where we let the region grow the way it grows naturally. Here is the forestation scenario, right? And both are in 2024. And here's the difference between the two, between the do nothing scenario and the forestation scenario. And you can see that the top colors, red, pink, up to yellow, are denoting losses, meaning there are fewer jobs in those locations, so we consider them losers. And the bottom part of the spectrum, between yellow, light blue, and dark blue, are winners, as it were, because they are actually going to get more jobs than predicted if we do nothing. So now I'm going to show you a few comparisons of specific cities. And first, I'm going to show you a few selected losers in the region. You can see that the little circles are the actual data. The red is the do nothing scenario, and compared to it, large cities seem to lose jobs. Not by much, mind you, but they do. They lose jobs, and they might not like that. And there are some smaller outer suburbs which are doing very well economically now, but have a lot of forests around, so they are candidates for forestation next to those existing forests, and they're going to be also losers. And in contrast, I'm going to show you 3 winners, and they are inner suburbs. In other words, they don't fulfill the conditions for forestation, so they're actually just getting jobs, and they're very happy about it. Here too, we have a smaller city that is actually a loser. In other words, it actually loses all the jobs by year 2024. And that's because it is good for forestation. So it's not different in size from the other 3 cities that are winners, but it's placed in a way that it's a candidate for forestation. So here is what we found. We found that in Northeast Ohio, there is enough commercial, industrial vacant land matching the forestation conditions so that we could propose to engage in this activity. We found some job winners with some suburban locations and some small rural areas. And we also found some job losers that are the largest legacy cities in the region, and some edge locations that I mentioned to you that are currently successful, but are also good for planting. And something that's important that we couldn't have guessed by just looking at the maps is that there's some loss of green fields, meaning that if there's some land where we can plant trees, but there's also some economic activity, jobs will go to those places. And that's a loss of pristine, nice places that might not be doing very well. Here are some of our plans for next steps. We're going to test land set-asides at different levels and in steps to see if we can mitigate the losing or even increase the winning. We are going to expand to some residential vacant land, maybe, just to see what the impact is. And this is our heart's wish to design an interface to enable what-if questions as we present this to stakeholders in the region. For instance, our transportation, metropolitan planning agency, and other decision makers in the region who might want to say, what if we did this? What if we did that? And we could probably show them that. So this is what I wanted to show you. Thank you for listening, and I'd be glad to take questions.
Thank you very much for your very interesting presentation. Are there any questions?
Can I ask? I'm sorry. Do you
For
hear me?
sure.
I just want to ask if I understood this right. So what you're showing that if you're doing forestation, you will probably in some places will need to insert or find ways to find new jobs. Is that?
Thank you for the question. We're not talking about how to mitigate. We're saying, watch out, these places are going to lose jobs. And the policymaker who is trying to maybe plant trees on the outside might notice that Cleveland is a loser. This is the biggest city in the area, and might say, whoa, wait a minute, nobody's going to let me do that. Let me see if I can do something about it. But that's not part of our model unless we get specific data, and then we can run the model with that assumption.
Okay, but your model can be used for that, so you can go with that and say, okay, but here you will have to do also this in order not to lose jobs.
Right.
Okay.
Exactly.
Okay.
Thank you for the question. Yes.
Thank you.
Thank you very much. I think there is no other questions. So thank you very much, and we should proceed to the next oral presentation by Kamal Rana. Oh,
yeah.
He's here. So Kamal will present the integrating climate network analysis with machine learning to predict South Asian monsoon.
Yeah.
So you may proceed. Please share your presentation.
Okay, thanks. Can you see my screen?
Yes. Great.
Hello everyone, I'm Kamal, a PhD student in Center for Imaging Science, and I'm working with Professor Nishant Malik from School of Mathematical Science at Rochester Institute of Technology. Topic of my talk is forecasting South Asian monsoon using machine learning and complex network. South Asian monsoon is the seasonal rainfall from June to September, and it occurs in this region, which consists of countries like India and its neighboring countries. As India is one of the largest countries and it is the one who is highly impacted by the monsoon. So hereafter I will only talk about the Indian region. South Asian monsoon is quite important as country receive around 70% of annual rainfall from monsoon. It also impacts agriculture as around 60 to 70% of cultivated land depends on rain-fed farming, which directly depends on monsoon. Because of monsoon, natural water resources like river, pond, well, and lakes are refilled with water, which provide water to the whole country for drinking and other purposes. Monsoons also affect employment as large proportion of population depends on agriculture. South Asian monsoon has a huge effect on economy and employment. Around 14% of the country's GDP depends on the agriculture that directly depends on the monsoon, and also around 45% of employment depends on agriculture. So just imagine if something goes wrong with the monsoon, it badly affects the people. Because of such huge importance, monsoon is also called real finance minister of the country. South Asian monsoon can be divided into three ranges: normal monsoon, above normal monsoon, and below normal monsoon. During normal monsoon, the farming output is good, that makes farmer happy. Natural water resources are refilled with water that fulfill the need of water. Farmers earn a good amount of profit by selling their crops. Because of such good reason, it is also called life bringer. In below normal monsoon, country receive very less amount of rainfall. In some part of the country suffer from drought and farmer does not able to grow crops because of no other irrigation option available. In some part, people face a lot of difficulty to get drinking water, and the picture express their difficulty in getting water. In some regions of country, especially poor people have to travel a lot to get water for their daily drinking purpose. Because of such reason, below normal monsoon, also called life taker. In above normal monsoon, country receive excess amount of rainfall. In some regions, roads are filled with water that affects day-to-day activities. Some regions even receive flood that damage the whole area. Because of many people become homeless and even some people died. Because of excess rain, farming got damaged that affects farmer and the whole country badly. Because of such reason, above normal monsoon is also called life taker. So far I have talked about the importance of monsoon and its effects on the country and its peoples when it is abnormal. We can mitigate all the losses occurred due to abnormal monsoon by forecasting monsoon in advance so that policymakers and people can take steps in advance. We have developed a method that can forecast monsoon in advance by around 45 days using complex network. We have used surface air temperature data in the globe that is measured at atmospheric height where 99.5% of the surface air pressure is maintained. The data span from the time period 1948 to 2009. It has angular resolution of 2.5 degree in both latitude and longitude, and it has total number of 10,512 grid points. Here each point represents a grid point. There is an issue with the data that it is regular in both latitude and longitude. That leads to more spatial distance between any two neighbors in equator than the poles. So to avoid this, we project the data into isohedron grid, where the distance between any two neighboring points is almost same everywhere. So here each grid point represents a time series from 1948 to 2009, and it has a daily resolution. We construct co-evolving networks by using truncated time series of 1 year and has an offset of 30 days. So we find the correlation of the truncated time series of any two grids, and if the correlation between the two time series is above a threshold, we add an edge between them. So in such a way we construct a network. So this is an example of one of a network, of the constructed network. We calculate different measures for each network, like degree. So degree tells how many edges a particular node have. So in this case, this node have 4 edges. So degree is 4. Local clustering coefficient. So it is the ratio of total number of edges between neighbors of a node to the total possible edges exist between the neighbors of a node. So here there is only one edges between the neighbor of this node, and there are 6 possible edges. So the clustering coefficient is 1 by 6, and average link distance is the average distance between the neighbors of a node. This is the degree plot for 2 different time interval. As we can see that it has different pattern for each time period. So the underlying dynamics happening in the globe is embedded in this network measure, and we can use this network measure to forecast climatic phenomena like South Asian monsoon. We train our algorithm using different climatic measure like degree, local clustering coefficient, and average link distance. We train the algorithm from 1948 to 1996 data and test it from 1997 to 2009. Here, y-axis tells the amount of rainfall in millimeter, and the x-axis has year, testing years. Here Q1, Q2, Q3, Q4 are the different quantiles range. Here we can see the observed and the predicted rainfall is quite near, and there was around 5% deviation from the actual rainfall. We use extra tree regressor, which is a decision tree based method. Our method is also able to calculate the drought, which the previous methods were not able to calculate. Forecasting intra-seasonal variation of monsoon also plays a vital role. There are cases when the mean seasonal monsoon is normal in past years. However, monsoon onset delay and unusual sudden break in have drastically affected agriculture and water supply. So we have also forecasted monsoon for each monsoon month. So here y-axis has the testing years, x-axis has the testing years, and the y-axis has the rainfall in millimeter. So for each monsoon month, the percentage deviation was around 10%, and for most of the testing year the prediction was good. However, for some particular year the prediction was not good. So for example, for June 2009 the prediction was very bad. for 2002, July prediction was quite bad, and in case of September, the 2001 rainfall prediction was quite bad. Monsoon rainfall across the country is not uniform due to the geographical diversity. The country geographical diversity is extreme with snowy Himalayas, deserts, hilly areas, plains and islands. Hilly regions of the country receive much higher amount of rainfall than the deserts area. So it is also important to forecast monsoon in different regions individually. So we have forecast monsoon for 45 regions, and we have calculated average deviation, median deviation, correlation and performance parameter between the actual and predicted out rainfall. So here performance parameter is ratio of mean square error to the standard deviation of the actual data. So we got decent results for most of the region except the region which consists of deserts like Rajasthan and some eastern areas which consist of mountains. So in conclusion, we have forecasted mean seasonal monsoon, intra-seasonal monsoon and the region-wise monsoon for the country India using complex network and machine learning. Yeah, thank you. These are the references and thank you.
Thank you very much. Are there any questions? Well, I suppose that it's quite late for questions. So since there is no questions for the moment, I would like to thank the speaker. Thank you very much.